My name is Vedan Joshi, and today I'm going to talk about the need for context-aware adaptive control for energy-efficient HVAC systems. Buildings across the world consume a significant amount of energy, which is equivalent to one-third of the total energy produced. This has led to a lot of challenges regarding depleting energy resources and increasing building service demands. The International Energy Agency is pushing to improve HVAC efficiencies by 50% to achieve sustainability goals. Another challenge faced is that ventilation systems, especially in office buildings, do not provide desired thermal comfort to all subspaces. They are often inefficient, and replacing them can be extremely expensive. We decided to address these challenges by computationally analyzing a three-room office configuration as shown in the figure below. The domain for the study has two exterior rooms that are subjected to a solar radiation of 350 watt per meter square and an interior room with no windows. Rooms B and C have shaded windows that transfer heat via radiation and conduction. Each room is occupied by a person and has a diffuser which uniformly supplies conditioned air at 120 CFM. This model was inspired from a real-life scenario where thermostat in room A controls the diffuser air supply for all three rooms, and the preferred set point temperature was 22 degrees Celsius. The methodology for the study involved solving the transient equations for conservation of mass, momentum, and energy, where natural convection was modeled using the Bose-Nash approximation, which treats density as a constant except for the force term in the momentum equation. The CFD simulations were conducted using the pressure-based Navier-Stokes solver in ANSYS Fluent, and the turbulence in the computational domain was predicted using the realizable K-epsilon model. Radiative heat transfer through the semi-transparent windows was solved using the discrete ordinate model, which acted as an additional source of heat for the exterior rooms. To minimize the discretization error, a grid-independent study was conducted using four grids as shown in the table. Mesh 3 with a grid convergence index of 0.18 was used to mesh each room with refinements near the vents and the occupants. The CFD model then was validated by replicating experiments done by lumens. To examine the efficacy of using distributed temperature sensors to control the operation of the HVAC system, three scenarios were simulated. The first scenario models a conventional system where a wall-mount thermostat in the interior room controls the on-off operation of the diffusers for all the three rooms, and the air is supplied uniformly in all directions. The next scenario examines the directional diffusers that use contextual information from distributed sensors to control the HVAC operation. The distributed sensors allow the ventilation system to adapt to changes in the room. For the second scenario, the HVAC operation is controlled by the average temperature of all the occupants, whereas for the third scenario, each room is independently controlled by a thermostat placed near the occupant. The conventional HVAC system is controlled by a thermostat in room A, and the doors between the rooms is assumed to be closed. The temperature contours at the neck height 60 minutes after the HVAC operation shows that rooms B and C are at a higher temperature than room A. The temporal variation of average room temperature shows that the exterior rooms are always warmer than thermal comfort levels, whereas the average temperature of room A is consistent with the thermostat set point temperature. The higher temperature in room B and C is because of the excess heat from the sun. Moreover, the diffuser in these rooms supply a portion of air towards the wall. This air can be utilized more efficiently to condition the additional cooling requirements. Due to the uneven distribution of thermal load, the cooling time for rooms B and C is more, hence the diffusers need to remain on for a longer duration to provide thermal comfort to occupants in those rooms. To improve thermal comfort and to eliminate the bias of measuring temperature in only one subspace, the combined average temperature of all three occupants is used for context-aware control. This provides a better cooling in rooms B and C and reduces the temperature in room A. The average temperature in rooms B and C reduces compared to the conventional scenario. However, occupants do not experience thermal comfort because of the continuous solar radiation. The average cooling time is more for this scenario, which indicates that system is adapting to the additional conditioning needs required to provide thermal comfort in a thermally imbalanced office configuration. The temperature difference between room A and room B and C seem to increase with time, and occupant in room A may experience discomfort due to cold environment. Previous scenarios show that cooling requirements for all the three rooms are different because of the different thermal loads. Therefore, a different strategy is adopted where each room is independently controlled by the distributed sensor located near the occupant. A user-defined function was used to communicate between the diffuser and the thermostat location near the occupant. Entire flow of the diffuser is directed towards the occupant to provide personalized thermal comfort. The temperature contours at neck level show that thermal comfort was achieved in all the three rooms. The blue patch in rooms B and C show that the conditioned air is being directed from the diffusers towards the occupant, which ensures efficient utilization of cool air from the HVAC system. The temporal variation of average temperature shows that the three diffusers turn on and off asynchronously. Additionally, room A has the shortest cooling time and the longest heating time, as the only heat source in the room is the occupant. Results show that the average cooling time for room C is the largest, as it has a large window which allows more solar radiation to pass through compared to room B. The primary goal of using directional diffusers is energy conservation while maintaining thermal comfort. To quantify the extent of thermal comfort achieved, we defined temperature discrepancy, which is the difference between the occupant temperature and thermostat temperature. The value of discrepancy must ideally be zero, which would imply that the occupant is at its preferred thermal state. The table below summarizes the discrepancies experienced by occupants for all three scenarios. Scenario 1 has lowest discrepancy for occupant in room A, as thermostat in that room controls the HVAC system, which results in a higher discrepancy for occupants in rooms B and C. Scenario 2 improves the thermal comfort for occupants in rooms B and C by putting the occupant in room A to discomfort. However, Scenario 3 has low values of discrepancies for all three rooms, indicating that thermal comfort is achieved for all occupants. The overall discrepancy is lowest for Scenario 3, which implies an improved overall performance. To quantify the energy consumption, the total volume of conditioned air supplied to the thermal zone is calculated. The energy consumption, or TSCA, is minimum for Scenario 1 and is maximum for Scenario 3. However, Scenario 1 does not achieve the primary purpose of providing thermal comfort. Therefore, to understand the efficient utilization of air, a normalized TSCA is calculated, which accounts for the energy consumption and temperature discrepancy. The value for scenario 2 and 3 are reported relative to the conventional scenario and shows that TSCA norm is lowest for scenario 3. This implies that using directional diffusers with independent control utilizes the conditioned air from HVAC system efficiently. In conclusion, the simulations showed that rooms require different conditioning time depending on their thermal load. Therefore, conventional HVAC system fails to provide thermal comfort when thermostat in one subspace controls the HVAC operation of the entire space. Distributed sensors provide additional feedback to control the HVAC operation and can improve the fairness of thermal comfort where thermal load is imbalanced. Directional diffusers have the ability to change flow direction according to the dynamics of the occupant and conditions in the room, and when independently controlled, increase energy efficiency of the HVAC system. These strategies can be adopted by buildings to decrease energy consumption without replacing their existing HVAC systems. This work was performed in part at University at Buffalo's Center for Computational Research facility. The authors would also like to thank the Department of Mechanical and Aerospace Engineering at UB for their financial support.